Lesson 6.2, rational exponents. What does rational mean to you? What are they talking about when they say rational? What should you picture?
Easy to work with.
Easy to work with. Oh, you like rational. Okay. So rational, in a context of probably the everyday world, we say if somebody is a rational person, they're easy to work with. In the mathematics world, is that what that means then? Rational means easy to work with. You see the word rational, like, yes, these are going to be easy. No, it should move. His phone is not silenced. It should mean what? Ratio. It comes from the word ratio. What do we think of when we think of a word of ratio? Fraction. So that means we're going to have exponents that are what? Fractions. And that should have been clear to you. You were supposed to read this lesson. Even if you didn't SQ3R totally, you should have applied, right? Rational exponents means we're going to deal with fractions. And so we're going to be challenged with how do we find a base taken to a fractional power? How do we do that without our calculators? Because your calculators are fully capable of it. They're really good at it. So we have the expression, oops, I guess I need a pen. We have the expression n in that little crook there, square root of b, and b raised to the 1 over n power, they mean the same thing. So no matter which way they're written, they really mean the same thing. Here's what it's asking. What number times itself n times gives you or is b? We call n the root. What root do they want you to find? Or in other words, that number that we're looking for times itself, what's the root? So n is the root and tells us which root of b we need to find. So we can find, we're most familiar with finding the square root of something up to this point, aren't we? And what's the square root of 9? 3. Square root of 81? 9. So you know how to find the square root really easily, don't you? We're familiar with that. So what would n be in the square root situation? 2. Square root means find what number times itself twice gives you what you're finding the square root of. So you and I said, what's the square root of 9? And you said 3. You're saying that 3 is the root of 9. 3 times itself gives you 9. When I asked you for the square root of 81, the root is what? 9, because 9 times itself is 81. Okay, so let's practice a little bit here, because how are we going to show work? Because I don't really want you using your calculator, because if you do, I can't go home with you and sit over you and say, you know what, you can't use that calculator. But what can I do is when you take the assessments in here, I can allow you not to use it. So if you're using it at home, and then when it's time to take the quiz, that's not going to be very helpful. So how can we show work for it then? So a to the 1/3 power. Instead of keying that into our calculator, we would say, that's really asking me for the 3rd root of 8. Or in other words, what number times itself 3 times is 8? That's what it's asking. What number times itself 3 times is 8? Anybody think they know what that is? 2. 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 2 times 2 times 2. 2 times itself 3 times is 8. So therefore we say that 8 to the 1/3 power equals 2. 8 to the 1/3 power is 2. Or in other words, the 3rd root of 8 is 2. Okay. Number 2. 81 to the 1/4 power is really asking for what? Which root? The 4th root. It's really asking for the 4th root of what? 81. Well, then that means, if it's asking us for the 4th root of 81, It's really saying what number times itself 4 times is 81. So it's kind of like we say, oh, I got to find something that when I multiply it out times itself 4 times, I'm going to get that 81. Well, is it 2 times 2 times 2 times 2? How do we know for sure it can't be 2? Abby?
Wait, what?
Well, how do we know that it can't be 2? Right away, just looking at the...
Oh,
Go
because
ahead.
it's odd.
This is not a number. 2 to any power is always going to be even, so it can't be 2. The fourth root of 81 can't be 2, so then we maybe just move up to the next number, the next integer, and say, could it be 3? Yeah, 3 times 3 is 9. And 9 times 3 is 27, and 27 times 3 does just happen to be 81, doesn't it? So we're going to say that 81 to the 1/4 power equals 3. Now, I'm going to let you take your calculator and check that out. Okay. 81, raise it to the 1/4 power, and let's see if we're right. Or am I misguiding you? No, it's right. Okay. So any questions so far? Now, your calculator, if you have your calculator, you might need to know how to put it into it also. You might need to do the parenthesis 1 divided by 4 thing, right? That's how I do it because I don't use fraction keys on calculators, so. Okay, let's look at number 3. We have an addition problem to do of rational powers here. We have rational exponents. So this is really, I just rewrote them as radicals instead. So I wrote 21 to the 1/2 power is really asking me for the square root of 121. So I can write it with the radical sign, 121. Now notice, there is no number written up in this area right here, is there? That's the only root that they don't ever show because it's an understood root. If there's not a number there, we're looking for the square root. That's what it means. If there's not a number there, you're looking for the second root, the square root of that number that's underneath that radical sign. So we're looking for the square root of 121. Let's just start there. That means we have to find something times itself that equals 121. What is that? 11. Yeah. 11 times 11 is 121, so this becomes 11. And then over here, fourth root of 256 means we have to find something that multiplied by itself 4 times gives us 256. Could be 2, because it's an even number. Is 2 times 2 times 2 times 2 256? No. Well, we already know that 3 to the 4th power is 81, don't we? So that only makes sense that this is going to be bigger than 3. Abby, what do you think?
Never mind.
Let's go to 4. Let's just try 4 then. 4 times 4, class.
16.
16. 16 times 4. Oh, you're stretching here, aren't I? 16 times 4 is 64. 64 times 4. 256. Yeah, we found it. 4 times 4 times 4 times 4 is 256. Or in other words, the fourth root of 256 is 4. And now what's our final number? 15. Okay. So you have a couple of options here. You have a couple of options for showing work. I need you to pay attention to me here because if you come tomorrow and you go straight from 121 to the 1/2 power plus 256 to the 1/4 power, and you say it is 11 plus 15, and then you have, or 11 plus 4, I mean, and then you get 15, and that's it. That's all you have. I'm going to be like this. So here's what they did. They put 121 to the 1/2 power on their calculator, and they got 11. They put 256 to the 1/4 power on their calculator and they got 4. And that's, so you actually have a couple of ways of showing work for this. You could do what I did right here, just show at least that much, to show that you understand what it's meaning. But I'm thinking this is going to make more sense to you. show that. But you have to show something that verifies that, you know what, you're not really just letting the calculator do all the work. Because it's so capable, trust me. As long as you can key it in for it. Any questions? Okay, 27 to the 1/3 power means we're looking for what? The third root of 27. 1 to the 1/5 power means we're looking for the fifth root of 1. Or in other words, okay, so now here's our showing work, okay? We could show this one, and we could say, okay, I'm really looking for the third root of 27 and the fifth root of 1. Or I could show I need something times itself 3 times, that will give me 27. I need something times itself 5 times, that gives me 1. So what is the third root of 27? 3. 3 times 3 is 9, 9 times 3 is 27. So this is 3. Fifth root of 1. 1. 1, 1, 1, 1. 1's the only one that you keep multiplying it by itself. I don't know how many times you do it, what are you always going to get? 1. So any root of 1 is 1. That's pretty handy, isn't it? Okay, 3 take away 1 is 2. Our final answer is 2 for this one. Okay, anything we should talk about? What did you notice so far with our fractions? What's always true in our fractions that we've done so far? Well, they're all positive, yeah. Good news is I'm going to only make you work with positives. They're what? They're all whole number. They have whole number numerators, you mean, and whole number denominators? Is that what you kind of mean? Okay, yeah, they all have whole number numerators and whole number denominators. What else?
There's always a 1 on top.
There's always a 1 in the numerator, isn't there? So notice we get to do this when there was a 1 in the numerator. We get to just say to ourselves, this is just asking me for that root. Whatever the denominator is, it's asking me for that root. Well, what if the numerator is not 1? What if it has a numerator other than 1, such as on the back side? When the fraction exponent has a numerator that is a whole number greater than 1, we can break it up and write it as a power to a power. Remember that chapter when we were exploring the properties of powers? What we do when we are adding bases, powers that have the same base, when we're subtracting powers that have the same base, when we're multiplying powers that have the same base. Anybody remember this? Dividing powers with the same base, taking a power to a power, a product to a power. You have all that in your repertoire already. You already have that. So now what we're going to do is we're going to use that. We know what to do with a power to a power. You take the exponent. You take that power, you take the exponent times the power it's being taken to. So I'm going to take b to the m over n power. That's just algebraic language. B is the base, m over n is the fractional exponent, with m being the numerator and n being the denominator. We're just going to take that, we're going to break it apart and say that would really be the same as b to the 1 over n power. And notice because remember, we already know how to do these when the numerator is 1. And then that is taken to the m power. Because remember, a power to a power means multiply. So is 1 over n times m, would that get us back to m over n? Yeah, so we're just breaking it apart. We're kind of like undoing it. So what this is really looking for is the nth root. Remember, it's right here. The nth root of a number raised to the m power. We're looking for the nth root, the denominator. We're looking for whatever the denominator is. That's the root we're looking for of that number. And then we have to take it to the numerator's power. Okay, so let's practice this. 16 to the 3/4 power. Notice I already broke the first one apart for us. it is the same as 16 to the 1/4 power raised to the 3rd power. Okay, so what they're asking us for here is they're asking us for the 4th root of 16, aren't they? So they're saying, what times itself 4 times equals 16? It's 2, isn't it? Yeah, 2 is that number. So 2 times 2 times 2 times 2, that is 16. So now what we had in parentheses actually became 2. And those parentheses really aren't very important because that's not a negative number, is it? So now we just say, what is 2 to the 3rd power? 8. And there's our answer. Now let me help you recognize something. And maybe this will just go way over your head. Or maybe, don't be working ahead for a moment. Stay. This may just go like, oof, I have no idea what she just said. Or you might be like, oh, that makes sense. It's 16 to the 3/4 power. Well, notice something. If I would have gone 3/4 of the way, 3 of the 4 of them, what's 2 times 2 times 2? 8. So if it had been 16 to the 2/4 power, I would have only gone 2/4 of the way, which would have just been the 2 times 2. And what is that? 4. Oh, and by the way, does 2 over 4 simplify to 1/2? And what is 16 to the 1/2 power? No, it's something times itself twice. It gives you 16. It's 4. Okay. And 16 to the 1/4 power? It's 2. 1/4 of the way over, and it's just the 2. Okay, again, that could have just like, oh, that doesn't make any sense. Don't even go there, Lagrange. Just, you can ignore that if you want. Okay, 25 to the 3/2 power. What's the first way we're going to write that? 25 to the 1/2 power, in parentheses, raised to the 3rd power. And this is the kind of work you absolutely have to show. You have to show me breaking it apart like this. Otherwise, again, I just have to believe that your calculator got to do it all for you. Anybody want to, no, I think I'll leave it alone for a moment. I'm going to have you make a prediction if you think the answer will be bigger than 25 or smaller than 25. Smaller? Bigger.
Bigger.
Okay. So, anybody, you want to justify, Jacob, why you think smaller, or is it just kind of a guess?
No.
Okay, I got lots of biggers, though. Why are you guys saying bigger then? Okay, because you just wanted to, challenge Jacob, right? Okay, well, let's see. Let's see what happens. So, 25 to the 1/2 power really means what times itself twice is 25? 5. Okay, so 5 times 5. So that tells me I have 5 now. And it's not a negative number, so I don't have to put it in parentheses, do I? Because I'm going to take it to the 3rd power in it. And it's not negative, so I can leave those parentheses out if I want. What's 5 to the 3rd power? 125. Oh, it did get bigger. Now, do you think you know why it got bigger? Well, maybe after we do that, we'll be like, oh, well, this makes sense now why it's doing that. Okay, let's do the next one. 27 to the 4/3 power. How would we first write that? 27 to the 1/3 power. Remember, the denominator is the first one that gets used. And that gets raised to the 4th power. Okay. So what we're really looking for when it's 27 to the 1/3 power, we're looking for what? What number? The 3rd root. So what number times itself? 3 times. Here's what your brain's going to want to do. You're going to want to take 27 and just divide it by 3. Think we're going to get the same answer if we do that? No. You're going to look for what number times itself 3 times gives you 27. And what is it? 3. And notice 27 divided by 3 is not 3, is it? No. So 3 And it's a positive number being raised to a power, so we can just leave the parentheses off. 3 to the 4th power is 81. Okay. Let's try the next one. We have 1 being raised to the 4/5 power. Well, that really means what?
It's one.
It's 1.
1 to the
1 to the 1/5 raised to the 4th power. So in other words, it's asking us for the 5th root of 1. What is that? 1. And it's positive, so I can leave the parentheses off. That has to be raised to the 4th power. And 1 raised to the 4th power is 1. So are you pretty convinced that we can just conjecture that no matter what power we raise 1 to, it's going to be 1? How about a negative power? How are you feeling about that? What if it's 1 to the negative 2 power?
Yeah, it's still.
It's still 1. Okay. 1 to the negative, I'm just going to go over here and do it. 1 to the negative 2 power is the same as what? 1 over 1 squared. And 1 squared is 1. And 1 divided by 1 is 1. So do you think we can conjecture, and then you can not have to show work for these, and just, should we just conjecture, should we all agree that 1 to any power is going to be 1? Even the 0 power?
Yeah.
Yeah. Even to the 0 power. Any non-zero number to the 0 power is always 1. So we get to conjecture that, you know what, we're feeling pretty confident that 1 to any power is 1 until somebody disproves it. So I'm going to let you out of show and work for these. Okay? Is that cool? Okay. 0 to the 5/6 power. That really means what? 0 to the 1/6 power raised to the 5th power. So this is really asking us what number times itself 6 times gives you 0. Well, it's got to be 0, doesn't it? So we're really saying that 0, because so we really have 0 raised to the 5th power, and 0 raised to the 5th power is 0. Okay, can we conjecture anything about 0, you think? Can 0 be taken to a negative power, do you think? Devin, did you have a question? I don't know, that's what we're trying to decide. And we just did showing work for this one also. Well, we got to decide, can we? So do you think that if you take 0 to any positive power, it's always going to be 0? Yeah, I think I can agree with that. How about 0 to the 0 power? Oh, that's going to be 1? That's a non-zero number being taken to the 0 power. Let's try 0 to the 0 power on our calculators. What is 0 to the 0 power? Undefined. Domain error. In other words, you can't do it. Okay, well then, how about 0 to the negative power? How do you feel about that? You think 0 can be taken to a negative power?
No.
Would you try it? Take any negative number you want, I don't care what it is. Error on Courtney's calculator. Error on Jared's calculator. Oh. So, what can we conjecture here?
0 to any positive power is going to be 0.
Yeah, 0 to any positive power is going to be 0. So can I let you out of showing work this to a positive power? Absolutely, yeah. Okay. So, and the chances are I won't do any of the others. But. So yes, Devin, we get out of showing work for this one. As long as it's to what power? What kind of a power, Devin? No. As long as 0 is being taken to what kind of a power? A positive power. As long as 0 is being taken to a positive power, we can get out of showing work. 4 to the 2.5 power. What in the world? Simplify. What do you mean simplify? Oh, rename 2.5. It's not really simplifying it because it's just changing it to an improper fraction. So it's really the same as 5 to the 5, or 4, excuse me, to the 5/2 power. 2.5. We're going to revert it back to its improper fraction name. And then we're going to say, okay, now I know that that can be rewritten as what? 4 to the 1/2 power raised to the 5th power. So this is really asking us for the square root of 4, or what number times itself is 4? 2. So we get 2 to the 5th power, which is 32. Some of these will start, getting up here. You'll be like, oh, I can do this without my calculator. Okay, are we clear on what kind of work we need to show? To show that you're really learning this stuff? Letting the calculator read the smarty pants? Okay, let's turn in your books then to 399. You probably, those of you who actually did SQ3R and stick it out, probably have already done this, but let's see how you did on it then. Okay, we are supposed to find the number of calories that an 81 kilogram panda needs each day. Well, I'm going to guess this must refer back to a different problem, huh? Probably example 3. In example 3, they say the approximate number of calories, capital C, that an animal needs each day is given by C equals, let's just write that down, C equals 72 times M to the 3/4 power. Where M is the animal's mass in kilograms, so that M is representing how much does it weigh, and C is representing what again? The number of calories. Okay, so find the number of calories that an 81 kilogram panda needs each day. So where are we going to put that 81 in? For M. Okay, so let's substitute in. So C equals 72 times 81 to the 3/4 power. Okay. What comes first in order of operations? Do we do that power first, or do we multiply first? Power first. And when you say parentheses, in this case, the parentheses are really just showing multiplication more somewhat and taking to a power. But in reality, what we have here is we have two things going on. We have a multiplication and we have a power. So which one should we do first? We should do the power first. So we're going to bring that 72 along, and we're just going to put a multiplication dot there now, and we're going to say, okay, this can be renamed as 81 to the, I don't need a parenthesis anymore, it's being taken, oh, I am eventually going to need one, I guess here. So 81 being raised to what power? 1/4 power, and then that gets raised to the 3rd power. So now, again, we're just going to bring C and the 72 along, and we're going to say, what is the 4th root of 81? By now we've got it memorized, don't we? What is it? It's 3. The 4th root of 81 is 3, so we show that that becomes 3. And so now we have 3 to the 3rd power. And 3 to the 3rd power is 27, so we have C equals 72 times 27. Holy cow, it's looking like this panda bear is going to get a lot of calories, Steve, huh? Yeah, lucky guy. Okay, so I will let you use your calculator now. 72 times 27 equals 1,944, and we give it a label, calories, because we know that's what it's representing. Okay. So, any questions on the application problem we did? Okay, does order of operations matter? Absolutely. That's the panda bear might like to do that in the order of operations, and way back even more calories than that. So, there.